we have a presenter here. Joe is an Apple AI/ML scholar in his 5th year of PhD. He is doing PhD at Imperial College London. His supervisor is Mary Reed. His research mainly is about creating robust and interpretable NLP models. So today he will mainly talk about two things. He will discuss how to improve robustness of NLP models, and he will also talk about how to make models interpretable inherently. So let's all welcome. Thank you all for joining us.
Thank you so much for having me. Really excited to be here. Thank you. So thank you for the introduction. So talk will kind of be in two parts. I'll first talk about model robustness, then I'll talk about creating interpretable models. Just briefly about me first and my background. So my background isn't actually computer science, a bit of a different background. I was a maths teacher in a very rough school for a number of years, and then I was a consultant for 6 years after that. So quite a different background. I quit my job and started a PhD, and absolutely loving it so far. I love teaching and presenting, so it's really nice to have this opportunity. And sorry for my strange accent as well. I hope I'm going to be easy enough to understand. If I talk, sometimes I get kind of enthusiastic and I start talking too quickly. Please tell me to slow down. I honestly won't be offended. Okay, so as I said, first part will be about creating robust models, second part about interpretability. The focus of my PhD has been on a task of natural language inference. Has anyone come across NLI before or studied NLI? If you have, you give me a little nod. Okay, cool. So most people haven't. That's fantastic. Essentially, it's quite a simple task. You have a premise, you have a hypothesis, and you have to decide, does a hypothesis contradict the premise, or does the hypothesis, is it implied by the premise, in which case you have entailment, or is it neither implied nor contradicting, in which case you have neutral. Okay, so contradiction, entailment, or neutral. So it's three classes. So let's look at this example. A person jumps. Horses. Okay, it's quite relevant because I know that horses are kind of really big here. Person on a horse jumps over a broken down plane. Hypothesis: a person is training their horse for competition. So what would we say the class for this would be of the three? Contradiction, entailment, or neutral? What do you think? Yeah, exactly, right. It doesn't contradict it. It's not implied, so it's neutral. It may or may not be true. Perfect. Okay, so first, talking about creating robust models. So there's been a lot of kind of older work looking at how models learn from shortcuts that aren't robust and don't generalize well to different data sets. And for example, in this task, NLI, if you have a negation word like not, models can learn and say, okay, I've seen a negation word, it's probably going to be the contradiction class. And that can lead to misclassifications. But actually, this is still an issue on very recent large-scale language models. So the paper last year, reversal curves, showed that if you fine-tune a model with the information that A is B, it can then recall, A is B, but not that B is A. So it's like this kind of non-robustness when you're fine-tuning a model with new information. So I think this is a really relevant problem. And in my opinion, there's not really a lot of research kind of trying to tackle this problem. So 3 things I'll address today or kind of talk about. Do we really need to fine-tune LLMs? Like, is there really a kind of substantial and worthwhile benefit? No, we have this kind of these drawbacks. Second, what's this trade-off between improving performance and this loss of robustness? And then, is there actually a way where we can improve robustness of these fine-tuned models? Yeah.
You say, do we really need to fine-tune modern LLMs? Is that just in the context of NLI, or is it a general question for LLMs? All applications?
Great point. I've just looked at NLI. So specifically, I've looked at, well, like, what's that difference in performance between few-shot prompting and fine tuning? Okay, now kind of going back in time a bit, some older work. I know this feels like a really long time ago now, but so 2019 to 2020, there was kind of work looking at, well, how do we stop models learning from known biases? So we talked about kind of negation words, or could be kind of an overlap of words between the hypothesis and premise, which means they're more likely to be entailed. And what you can do is you can say, okay, well, how biased is each training example? And then weight the loss of each training example based on how biased it is. Right? So basically, you learn less from the more biased examples. Right? You can do other things like you can supervise the model to be more uncertain for more biased examples. And that, again, kind of tends to help robustness. But the problem is, well, actually, what if we don't know what these dataset biases are? That assumes we have some list, right, where we know, okay, these are the specific biases, but we don't normally, right? We don't know what these kind of heuristics normally are. Some later work, a few years later, where they look at kind of estimating what we think, which examples we think are likely to have biases. And you can do things like you can have a very simple model, and you can make predictions with that simple model. And if that simple model is correct, well, it's likely to be learning from a bias. It's kind of strange. Well, the idea is that like a very simple model, maybe like a one-layer transform model, it doesn't have the capability to learn the true task, right? So if the very simple model is correct, it must be learning from some kind of bias feature, some kind of shallow heuristic or simple correlation. Okay, interesting. What's the problem with this? So what do you think happens if you debias a model for a particular bias? So if you mitigate against one bias, what do you think happens?
Created as others.
That's right. What's that?
Created another bias.
Right, yeah, create bias. So we did some work with, and we did a whole paper on trying to understand the behavior of models when you debias them. If you stop a model learning from one bias, it just relies on a different bias. Oh, okay. This is clearly not ideal, right? So it's like in this paper we created a whole bunch of kind of carefully controlled synthetic tasks, and we kind of artificially injected biases into these different tasks. We said, okay, well, if we have two biases, debias against one, the model just simply relies on a different bias. In fact, we also tested performance on like an unbiased test set. What we found is that debiasing made no difference on the model's ability to understand the underlying task. It just stops it being distracted by specific features.
Sorry, can I ask a question? This is not anyway, can you say what you mean by bias? Because it's not my area, and for my way of thinking, the only thing LLMs learn is bias. Every single thing that they quote understand is bias.
Okay, it's a great question. I think that the term is used quite loosely, first of all. I think it's very hard to distinguish, what is a desirable feature versus a kind of a correlation that you don't want the model to be learning from. And it's simply the model's entire ability is based on lots of these different simple correlations kind of put together, right? I think in NLI, one of the really nice things is that because you have this premise and hypothesis, we know the task must be considering the interaction between these two inputs, right? So if ever a model is successful, can be successful only from one input, like the hypothesis alone, then we know for a fact that this like undesirable behavior, these are features that we just don't want the model to learn from. So yeah, it's kind of, I'm using this term kind of loosely, but I do know for this task that I don't want a hypothesis-only model to be successful. So there's kind of some way that I can kind of distinguish between them. Does that make sense? Yeah. Cool. Yeah, I think I've actually talked through the content of this slide already. So yeah, we created these kind of carefully controlled paths, injecting the biases. We found that the model debiased for one bias, it learns from a different bias. and it does no better at the underlying task. You ever played that game Whack-A-Mole? Yes, like something pops up, whack it down, like this. For me, this is now how I think about debiasing, right? That if you try and debias, it can introduce different biases, and I now don't believe that stopping the model, learning from these kind of shortcuts is as desirable, it is the right way to approach this. And like we said, like maybe the model's whole abilities are based upon lots of different kind of simple shortcuts that put together result in impressive behavior. So I've really changed how I thought about this idea. Instead of trying to stop the model doing undesirable things, my research has maybe more focused on, well, how do we create more desirable model behavior that will generalize better? My first idea was, okay, maybe we can make models learn from how a human would approach the task. Because humans, we should approach things more in a more way, a better, more generalizable way, right? So can models learn from how humans approach the task?
So isn't that where most bias comes from?
So would you mind just elaborating a little bit?
That humans bring our own preconceptions and expectations. So many of the data-based models simply capture the biases of humans.
Yeah, lots I can unpack there. I think, well, the first thing I'd say is that this whole task actually is very subjective. I mean, so for example, if you have an entailment example, typically it's because the hypothesis is very likely given the premise. But how likely should it be? There's no really clear definition. Actually, it's what a human would intuitively think is entailment. But actually, there's no kind of clear definition there. Also, on that point, kind of human biases, actually, a lot of the biases observed in these data sets are because you say to a human annotator, okay, can you create a contradiction example? And they have kind of certain strategies and ideas about how to do that. And the model can just kind of pick up on these. For example, like unification words. So yeah, I think but what I would say is that humans do generalize very well to a whole range of different tasks. So it's kind of, can we mimic this generalizability that humans have that models just don't have? That makes sense. Okay, this was the very first paper to look at using natural language explanations, so that's the kind of input from the humans, to improve model robustness, back in kind of 2022. When we did it back then, it seemed like a pretty wacky thing to do. Wow, really? Like, learn from natural language explanations? Now it's much more kind of commonplace kind of thing to do because LLMs generate explanations very nicely. But back in the day, this is kind of a bit wacky and a bit out there. So I'll talk about briefly what I did, and I'll talk about kind of maybe more modern approaches and maybe kind of opportunities for future work. What we did is we took these explanations from humans. Okay, for example, I've got my premise, hypothesis, and my human natural language explanation. And we said, well, actually, we want to supervise the attention in the model. So the model pays more attention to words that are in the human natural language explanation. For example, so, the word dog, sleeping, and swims all appear in the explanation. So they should be important words for the task. Yes, the human thinks they're important components of this explanation. So we then supervise the attention from the model to pay attention to these words. We say, a quarter of attention on the word sleeping, a quarter of attention on the word swims. Specifically, we supervise the attention from the CLS token of the BERT model in the final layer and make it pay more attention to words humans think are important. Does that kind of make sense? What happens? So we had small but statistically significant improvements on different OOD data sets. That's how I'm measuring robustness, and also on the test set as well. Okay, nice. It's a nice idea. The improvements aren't fantastic, but it's a nice idea. Oh, and kind of nice that if you actually look at the attention and you compare the attention from the baseline model without the supervision, you really can't see much of what's going on. It tends to set tokens, sometimes to punctuation, sometimes to stop words. In the supervised model, actually you can suddenly see, right, okay, I can see which words should be important for this given instance. This is a few years ago. I think maybe a more common approach now would be to fine-tune a model to generate a chain of thoughts or an explanation along with an answer. There's some evidence that fine-tuning a model to generate an explanation does improve robustness. The evidence is a little bit mixed. It tends to be a paper by Alexis Ross in 2022 found that it was beneficial for larger models when you have less training data. A more recent paper last year that looked at something similar. You might have seen, has anyone seen Divergent Chain of Thoughts? It's a very, very new paper. It's kind of cool. So the idea is that you fine-tune a model to generate lots of different chains of thought, so different kind of explanations, each with a different answer. You do that all in one go, and you also fine-tune the model to give kind of a final answer. It's almost like it can kind of try out a whole bunch of different possible answers, and it has to conclude what it thinks the correct answer is. That's been quite successful for in distribution performance on test set, but it's not really about, like, there's not that much evidence that it improves robustness. Where am I going with this? Most methods now about generating fine-tuning models to generate explanations are all about in-distribution performance. I think there's an opportunity to consider methods that improve robustness. So I think maybe there's more work we could have done here to think, well, actually, what's the right way to do this if our goal is to improve robustness and OOD performance? Maybe that's something that seems to be kind of missing with kind of a very, very recent work. Let's think of a different strategy. We talked about using human explanations. I don't know. Can we just fine-tune an LLM, or even just a few shots, in fact, let's few shot, use an LLM to generate new training examples for whatever domain we want to test the model. So yeah, just generate, let's say I want to apply my model on a legal domain, just generate data for that domain and fine-tune on that data. That would solve our robustness problem. We can just generate data and train on that data. What's the big problem? Why is this kind of problematic? Do you think? Yeah.
AI is slop.
Yeah, it's not. I guess that was my answer, but maybe kind of phrased slightly differently. Yeah, just the problem is that few shots, LLMs just didn't generate particularly accurately labeled data. So I can generate data for whatever domain I want, but the label may not be correct. So how can I overcome this challenge? How can I get better generated data? I'll give you very briefly 3 strategies. You could fine-tune your model, fine-tune your data generation LLM to give better, well-labeled data. Recent paper last year from Google that did this, but they still found 1 in 10 instances had a different label from what a unanimous human annotation said. Okay, so supervision can make labeling a bit better, but it's not perfect. I did some work last year where we said, I don't know, LLMs can generate good, like nice premises, nice hypotheses, nice text, but we can't be sure about the label. So maybe we use it as unlabeled data. And if you think, you know when you do knowledge distillation, where a student learns from a teacher model, you don't need labels for that, right? Because just whatever data you have, the student model just learns to replicate the teacher model predictions. So in this case, I said, right, when I do distillation, I'm going to include my unlabeled data, and then the student model just learns to mimic the teacher model on that new unlabeled data. So it's like, the student learns to mimic the teacher model, beyond the narrow training data and learns to copy behavior in kind of a more general sense. Or maybe you're probably thinking, oh, great, if you have a teacher model. Maybe I don't have a teacher model. In that case, you can use an ensemble of models and distill the ensemble into a single model, in which case, still using this unlabeled data from different domains substantially improves robustness. The second strategy. Third strategy, I love this name, gradient surgery. I mean, whoever came up with gradient surgery, I think it's like a marketing genius. I think it just sounds so nice, gradient surgery. Let me explain what it is. What they do is they have synthetic data and human annotated data. And when they do their backpropagation, they find the gradients from the synthetic data, gradients from the real data, so it's kind of paired. And they basically make sure there's no conflict between the two. So they project, try and get this right, they project synthetic gradients onto the direction of the human annotated gradients. If the dot product is negative, then they minus this projection. So basically, if there's any conflict between the two, they minus the conflicting component of the gradients. It's kind of cool. Here's some ideas you just think, oh, I wish I thought of that. That's one of those, I was like, yeah, that's cool. I really wish that was me and I had this gradient surgery method. Anyway, so a few different approaches. I'm going to go on a bit of a detour now into task-oriented dialogue, and then I'm going to kind of bring it back to what we're talking about. Okay, so I'm doing this 7-month internship with Apple. Tim Cook, by the way, there might be some exaggeration on this slide. Okay, so bear with me. Tim Cook says, Joe, okay, you're the new intern. I've heard great things about you. I want you to generate some really high-quality data for task-oriented dialogue. It needs to be complex, diverse, interesting, but you can't have any human annotation. I'm scared, it's the big boss, you know, and he's giving me this ridiculous task. I mean, how am I supposed to do that? No human annotation. But that's okay, Joe. Here is a giant pot of money. Okay, you spend that as you like. Money is no problem here. You know, so okay, interesting. What did I do? How can I overcome this? Well, the idea was, okay, let's generate loads and loads of data. And we had this this approach called if in doubt, discard, basically. If we have any reason to doubt a generated conversation, just chuck it away. Again, I don't care about money here. Just all I care about is what I'm left with. So, okay, first of all, show you the data. So it's like turn-by-turn data between user and an AI virtual assistant. The user request, then we label what the user wants. We then have a natural language response back to the user, and the kind of conversation keeps going, kind of multi-turn conversations. So what we did was, every single time the LLM generates a label, we did it multiple different times, sometimes giving different information to the LLM with a non-deterministic temperature value. And if there's any difference between any of the LLM predictions, we just threw it away. I can see some kind of skepticism in your eyes. I really threw it away. I mean, like, super wasteful, right? I mean, yeah, it's pretty wasteful, pretty expensive. But the result was, what I was left with was really, really high quality data. Because I knew, you know, a very conservative filtering, what I was left with, I knew was good quality. Oh, and the conversations were really fun. We had things like this example, they want to review a film, the virtual assistant says, what's the name of the film? The user says, okay, stop playing with food, eat your dinner. And it has to kind of detect, okay, well that's not the name of a film, right? That's just something overheard. So it's quite kind of challenging phenomenon. We just show a few others, different things. Okay, irrelevant information, the user just says something completely strange back. Let me pick out your, okay, sarcasm. So The virtual assistant, it's called Lucid, says, "Could you tell me the duration of your 5-mile run?" The user says, "It took me a decade to complete." So the virtual assistant has to pick up, okay, that's sarcasm, yeah, that's not a valid value, and then to respond back to the user and say, "No, can you please tell me what was the actual duration?" So it's pretty fun. But just very briefly, another kind of really crucial component of this was breaking down the data generation kind of really smaller steps. The idea is that if we break down the complexity of each LLM call, then we can rely on LLMs to consistently be accurate for the kind of smaller, discrete steps. And also, like, you think the more smaller steps you have, the more different validation you can do, right? Because again, all we cared about was what we're left with that is really high quality data. Yeah, there's a follow-on paper related to this. It's in SIGDAL this year. Yeah, and that explores a bit more. So one of the things the data we have is these kind of Pythonic representations, which are kind of quite convenient targets for an LLM. We also have like a mock backends that they interact with. So basically, like, the user says, "Okay, I want grocery shopping on the 10th of August. The system then labels that, and then the mock backend comes back and says, "Okay, cool, all the slots are populated. Yeah, and what's next?" So anyway, there's a paper to come that kind of goes into this in more detail. Right, anyway, let's come back to robustness. Is this still an issue with recent closed source LLMs? What I'm going to show you now is a table where I can compare a fine-tuned model on NLI to a few-shot model. And when I compare the fine-tuned model, I'm going to try fine-tuning with 5,000, 10,000, and 20,000 instances. So let's see. Is fine-tuning really important, and what happens to robustness? Right. So this is my in-distribution performance. Wow. It's a pretty large increase in performance from fine-tuning, right? It's like, what, 7 percentage points? That's really quite some benefit. Very interestingly, we look at robustness, or we look at the OOD performance, it's a really big trade-off. So yes, fine-tuning will help your in-distribution performance, but it really works against you when you look at your OOD performance. We evaluated on a whole bunch of data sets, challenging and less challenging. It seemed to impact more the most challenging OOD data sets. I don't know if anyone has any intuition about why that might be, or I'm not entirely sure myself. I think still trying to understand that, but yeah, this surprises me still. The scale of the trade-off, right? I guess the scale of improvements from fine-tuning, but also the scale of the loss in robustness. So it seems like a really important challenge that I don't think many researchers are considering at the moment. Let's go back to trying to improve robustness. What I'm going to do now is I'm going to use this if-in-doubt discard approach. I'm going to generate a whole bunch of data with LLMs for different domains, use my if-in-doubt discard method where I make lots of predictions and I throw it any way where there's any difference between different LLM calls. So does this new synthetic data improve robustness? Have a look. I've got 4 different methods. I'm not going to go into detail about what these are at this stage. Okay, so similar performance in distribution when I include this synthetic data. Doesn't make it any better for the challenging OOD data sets. But really quite big improvements for less challenging OOD data sets. Well, that's really promising, right? In fact, let me just caveat this with, we had a fixed training budget of 10,000 training samples. So we used GPT-4o Mini as a closed source model. It's pretty expensive. So we said, okay, well, 10,000 instances, that's like $5. That seems fair, right? So we said, okay, well, can we improve robustness with this fixed budget of 10,000 examples? So we generated new data, but then we replaced existing data to make way for that. This is always 10,000 examples we train with. Does that make sense? Kind of makes it kind of a fair like-for-like comparison. Right? So what's going on? Why is this successful on some OOD data sets but not on others? The real challenge is the complexity of the LLM-generated data. I don't know if anyone's experienced the same thing, but I found it really quite difficult to get complex, challenging examples from an LLM. And all the data generated was just too simple. I went through, I manually annotated these examples. I said, okay, every example, how difficult is it? Out of 10, 3, 4, you know. And I found that it just wasn't complex enough. Yes?
Can you talk a little bit more about that annotation process? So, like, measuring difficulty? Was it just you that went through and were like, I think this is a 6, or...
It was exactly that.
Okay.
I mean, like this is like analysis in the paper, right? So this is to try and quantify it. I guess to just kind of support what I was saying in the results. Yeah, great question. I guess you could probably do a whole paper around that.
Yeah, I was wondering, because, like, yeah, that's a hard problem, figuring out, you know, what is hard. But
In fact, there's a paper by Alex Gill from the University of Utah. Sorry, I get so excited presenting. And it looked at this. Their conclusion was that generating synthetic evaluation is just too easy for LLMs. If you generate data using an LLM and then test an LLM with that data, it's just really difficult to get the complexity. So it kind of maybe, yeah, you can probably write a whole bunch of papers on that topic.
how did this compare? Like, did you look at, there are automated complexity measures for sentences. They're not great, but, like, how would the output of an LLM compare on, like, that front, do you think? Like, are the sentences grammatically difficult by whatever this stupid measure says? Or, yeah.
Good question. I think, so there's one difficulty measure I know which is called MTL, which is like information theoretic way. I think it's quite involved to do that calculation.
Right.
So that's kind of, I guess, one we could go down. I would say that the difficulty is that the complexity is in how the sentences relate to each other.
Right.
So I think that might be quite hard to measure using.
Yeah.
Okay. Great point. I love questions. Okay, where are we? Yeah, so you can prompt an LLM to make more complex data. So the bottom row we try through prompting to make more complex data. Yeah, okay, like small benefit, but it's still difficult, right? So creating complex data with LLMs is still a real challenge. Instead, we looked at different strategies to create better robustness on these complex data. Our idea was, well, actually, let's still use that training, the given training data. Maybe can we pick more complex examples? So we have 10,000 training examples. Maybe we can just pick them in a better way, right? That kind of upsamples more challenging data. We tried a bunch of strategies. I won't talk through all the methods, but essentially, yeah, can we assess how difficult each training example is and then upsample harder ones so that you can use an LLM to rate out of 10, like I did, how difficult the example is, and okay, take the highest scores and then upsample those examples. You could you can fine-tune just the baseline model on the normal 10,000 examples and use that same model to make predictions on the training examples and see, well, which training examples does that model get wrong? Does that make sense as like an approach? So classically, just train twice is like, yeah, how referred to. Or even like, maybe you could use this model, make predictions on training data, but instead of choosing where the model is incorrect, choose where it's uncertain. Because if you think like, you could just have bad annotations, right? And so the uncertainty is a way to kind of to guard against that. Just very briefly, what we see, my sampling methods here in the middle, where we try to choose more complex data, and okay, now we start to see some improvements on the complex data. Not the same scale as we saw here, which were really nice improvements, but some progress. Although it's still quite difficult to make these improvements one more challenging LLD data sets. Before I move on to the second part, I think this is like some really nice opportunity for more work in this space. If you think you could beat my baselines, I would love for you to have a go. So maybe you can think of an idea that I've missed, or maybe like take this further in some way. I would love that. So yeah, if you're interested, yeah, I think it's a fun problem. Yeah, and maybe you can do better than my results. Okay, perfect. So that takes us to the end of part one on model robustness. I'm now going to talk about, can we create inherently interpretable models? By the way, has anyone done any research on interpretability in any way? If so, just give me a good. So got a couple of people. Great. I think it's super interesting. I hope you enjoy this next bit as well. There's about 2 of my ENLP papers, one from a few years ago. I know that you might think that looks quite old, but I promise you it's still kind of cool and interesting. And a paper from last year's ENLP. What's the motivation for this? Well, there's a whole bunch of different feature attribution methods where you can try and guess what the reason is for each model prediction. But there's no guarantee. I could generate a chain of thoughts, explanations that kind of suggest why the model made that decision. But I don't know if it's faithful. It's what the model actually did. I could use like gradient-based methods to see, well, what are influential features? Again, there's no guarantee, right? I don't know. Actually, they were the specific reason for the prediction. Another way to think about it is, well, rather than trying to explain a black box model, maybe we can create an interpretable model instead that hopefully will perform close to the same performance. In that case, an interpretable model would give us some kind of guarantee for why the model makes these predictions. There's a beautiful survey by Caldron and Ratchart from Technion in Israel, where they look at a whole bunch of different papers on interpretability, and they categorize how many papers are looking at which different interpretability methods. It's really fun. And one of the things they conclude is that there's very little work on these self-explaining, inherently interpretable models. And when there is, there's like a big trade-off with performance. So yes, you get interpretability, but if the model's not that great, then you're probably not going to use that way. Our idea is, we describe it as atomic inference. We define this as saying you make hard predictions for independent, different components, which we say are called atoms. Sounds cool. Different atoms of an input. Make these predictions independently, then use interpretable and deterministic rules to aggregate this together to an overall prediction for the whole input. Sounds nice, sounds sensible. But well, what are these atoms? How can you decompose an input? It's quite task dependent, it's not obvious. How do you actually make good predictions for each atom? Because you find you're training a model to be good at the task, and you probably have a label for the whole instance. But how do you make good predictions for each individual atom when we have no labels for each atom? So how do we get like kind of good performance at an atom level? And how do we kind of aggregate this together? What are our interpretable rules? A few interesting things I want to emphasize. So in this approach, or in this definition, you make hard predictions for each atom. There's some work that kind of decomposes things into atoms. They make soft they get some score for each atom, and they aggregate this together. Like maybe they take a mean or something. Is that really that interpretable? Kind of, but it's like, well, this atom contributes a bit, this atom takes away a bit. It's not so clear, right? If you have hard predictions, you can say, right, Well, I know this is hate speech because this specific atom is hate speech. That is clear interpretability. Also, we say you must make predictions independently for atoms. Several different papers, they make predictions for an atom, but they can see the whole inputs when they do that. But there's no guarantee then that that atom is the reason for that model prediction. So for this, we say the predictions for each atom must be independent. Because then we have our guarantee, right, that we know exactly why the model makes the predictions that it does. I know I spent a few minutes on this. I actually really believe in this approach, this definition. Like, I hope you agree that if your method satisfies this, it's like really strong interpretability. So yeah, I'm really a fan of this. Right, let's talk about how we apply this idea. In NLI, you can break down a hypothesis. We broke it down to spans, text spans. We said, okay, well, each span is an atom. Okay, here a man in a wetsuit walks out of water. A man in a wetsuit walks out of water carrying a surfboard. Well, the span that makes this neutral, like, does not apply, doesn't contradict, is carrying a surfboard. So if I break this into different spans, I can make a prediction span by span, and I'd say, well, this last span is neutral, and that makes the whole input neutral. So segment the input based on spans. That's the first idea from our original paper in 2022. Then you can evaluate using kind of simple rules like, well, okay, is there a contradiction span? Yes, the whole thing then must be contradiction. If not, is there a neutral span? The whole thing must then be neutral. Does that make sense? Well, I guess here, like, what's happening here, we have one neutral span. Because that bit isn't implied, the whole thing is not implied. So the presence of the neutral span means the whole thing must be neutral. I know this is kind of specific to NLI, but I'll talk a bit later about how you maybe could apply these ideas to different tasks. Okay, so we can aggregate together the predictions for each individual atom, that's fine. How do we train the model to make good predictions at atom level without any atom level labels? I like this, I think it's kind of elegant, something nice for this. What we do is we give our model each atom independently, in this case, a span by hypothesis, give this with the premise. I get a score for each atom, and then I supervise the maximum of these scores. Like, max kind of acts like a logical OR operator in a way. And so, for example, like, if I'm trying to detect, is there a neutral span somewhere, I can say, right, I know one of these spans is neutral because the overall thing is neutral. So I supervise the score for each span, take the max of those scores, and I say, oh, it must be close to 1. So I have a binary label saying 1 or 0, is there a neutral span? And I supervise the max of the scores to be close to 1. So this is kind of, I know this is kind of challenging to get your head around, and I'm asking a lot from you to get this straight away. So don't worry if you kind of half get this, because it's kind of, you have to think about it a bit. But it's cool because like, it's like semi-supervised, and letting the model decide for itself which span should be neutral. So we do the same thing for contradiction. Is there a contradiction span? Yes or no? We have a score for each span. Is it a contradiction or not? We supervise the max of those scores. So simple, kind of elegant, but it turns out to be very effective. So using this max supervision, we can train the model to effectively decide span by span what the labels are without any labels at the span level. So there might be some details on the slide I skip over, I hope you don't mind. In the paper itself, if you have a look at this, if you're interested in it, the method is a bit more complicated, but the essence is what I've explained. Okay? So if you understand what I've talked about, you understand what's happening. Just, to improve performance incrementally, we made it a bit more complicated. But don't worry, if you understand the last slide, you understand what we're trying to do. I've talked about these like rules that we follow, like if there's a contradiction span, the whole thing must be contradiction, etc. I was decomposing the hypothesis into atoms, right? What happens if you decompose the premise instead? In fact, you need a whole different set of rules, and our second paper kind of looks at that instead. But like, I love this. Like, I think this is like kind of something beautiful about the task of NLI, that actually these whole series of logical rules, like, just kind of inherently follow from the task itself. So yeah, if any component contradicts it, then the whole thing must be contradiction. Like, I really like this. I won't talk through the details. I'm kind of skipping over it, but yeah, to me, there's some real kind of beauty in these rules underpinning the structure of the task. My collaborator Haim, he says it's like giving a model explainability superpowers, which is nice. Because suddenly I can see exactly, definitively the reason for every prediction. So normally, example 2, like, okay, 2 women embracing, holding takeaway packages, 2 sisters hugging goodbye, holding takeaway packages after eating lunch. Normally, a model would just say it's neutral. I think it's neutral. My model says, okay, well, I definitively know it's neutral because may not be sisters, may not be hugging goodbye, and we don't know they just had lunch. And this isn't an estimate. This is the definitive reason for each prediction. I suddenly know exactly why the model makes the predictions down to the atoms that I define. So the interpretability is really cool. We've got a bunch of examples in the appendix. Yeah, it worked really nicely for interpretability, the guarantee. You're probably thinking, oh, that's nice, but how about performance? Like, you get some amazing interpretability, but does it really perform that well? Some small trade-off with performance compared to the baseline. Other interpretable methods have quite big trade-offs. This method, small trade-off. Why is it so good? What works so well? It's this max supervision I talked about before. What does that mean? Am I doing something wrong? Maybe. Move. Oh, thank you. I'm tuning it to something. Yeah, so the max supervision is just really turns out to be a very effective way of doing this. Conscious of time, I'll move through these last slides quite briefly. The second paper, we break down input into LLM generated facts. Because the span-based thing is kind of limiting in some ways, right? Well, what are the spans? How big should they be? How should I define them? Whereas now we can ask an LLM to summarize all the information in an input and treat each of these as our atoms, right? Kind of reason over each of these independently. And I know exactly then which atom or which piece of information is responsible for my model prediction. We actually, when we worked on this was before facts score and all this stuff using facts, generated facts, and we were like super excited. Oh, this is really cool. This is so novel, you know, generating fact lists. By the time we published, these papers were already out there. So I guess it's funny, like the field moves so quickly, right? You kind of blink and people already kind of published stuff on the same idea. But anyway, these facts work really well for this atomic decomposition approach. So it's got a very nice combination. I'll just briefly say about performance. Actually, we found that using LLM generated facts, the model does even better than the baseline. So suddenly we see a performance improvement. But this is really not about performance. Like, I want interpretability, right? It just happens that, like I said, this max supervision, this atomic decomposition is just very effective performance-wise. Why is it better? When is it better? Well, we found that if the task is sufficiently difficult for the model, then there's some benefit from this, performance benefit from this decomposition. It's almost like maybe like the extra structure is kind of helpful if the task is hard enough. But so with a better performing model, I think you'd see, same performance or maybe even worse performance than baseline, because I think it's all about, is the task hard enough for that specific model? Right, so where are we? Let's talk about different tasks. So I've talked a lot about NLI. I'm sorry if you hate NLI. I'm sorry for talking about that task too much. But like I said, I really believe in this idea of atomic inference. And let's think about VQA. Could you apply atomic inference ideas to VQA? What would your atoms be, do you think, if you broke this down?
Bounding boxes?
Yeah, right, exactly. We can have kind of patches or kind of boxes in the image, make predictions separately about each part of the image, and then we can definitively know, well, which part of the image is responsible for this prediction. Yeah, that's a really cool idea. Oh, so you can have them, and you're probably wondering, well, okay, well, what should these boxes be? How much of the image should be included? You can have, I guess, you can have like one for the eyes, or for the face, or for you have a whole bunch of different boxes that even overlap with each other. It's not an issue to have overlapping atoms. Like, that's not an issue at all, because you make predictions separately for each atom. And you might find that, let's say you had one box that's the eyes, one box that's the nose, whatever, one box that's the face. Some atoms will be too granular to predict, the task. In which case, you kind of want to find, well, like, what's the smallest box such that we could predict this for. And again, it's a guarantee for interpretability that for like that area of the image is the reason, what allows us to make this prediction. And I talked about the rules for NLI and contradiction if not neutral, if not entailment, whatever. It's kind of complex, right? I put the rules on screen. This wouldn't be that complex, right? It's like, does it answer the question yes or no? Does do any boxes answer this question yes? If there's one yes, the whole thing is yes. Like, actually, I think in NLI it's more complicated. Or even, let's say like hate speech, right? So if you're deciding is a tweet hate speech, you could say if any part of it is hate speech, then the whole thing must be hate speech. So actually, the rules around it are maybe even simpler than what I talked about. So like I said, I really believe in this idea of atomic inference. I think it's quite powerful. And I think it can be applied to a whole bunch of different use cases, which it hasn't been so far to date. And just my paper bingo. I think I've mentioned quite a bunch of my papers. So I've talked about using natural language explanations. I've talked about distilling, using the unlabeled data. We talked about when and why debiasing works. Like if you mitigate for a bias, what happens? The model learns from different bias instead. Talked about improving robustness for LLMs, generating data or choosing challenging training examples. Talked about my papers on interpretability, and I briefly talked about my workshop paper on task writing dialogue. If you're interested, please drop me an email. I'd love to chat about any of this if you'd like to talk more about any of this work. I've just left like 6 minutes of questions. Sorry. Please follow me on X or Twitter. I'm quite active. I'd love to follow you back. And I'd love any questions. Anyone? Any thoughts, questions? Yes.
Okay. So this is specifically about the last set of projects with the logical rules for interpretability. A lot of that seems like you were relying on the kind of pre-existence of these logical rules. That's where a lot of the interpretability came from. Do you ever envision a situation or a task where it'd be difficult to come up with that set of logical rules? Like everything that you said at the top was really straightforward. It's like, oh yeah, if this exists, then the whole thing must be. But it seems like maybe there could be a time when it's not that easy. am I wrong in that understanding, or, yeah?
Very interesting. So I think for NLI, it's particularly complex because of these three classes and like the hierarchy between them. I think for binary classification tasks, it's more often not quite simple. It's, you know, do we have this particular class like hate speech? If yes, the whole thing is hate speech. Some tasks are looked at kind of analogous to NLI in how this works. I haven't yet come across a task where you can't easily figure out what the rules should be. But if you do come across that, I would love to know, because I love a challenge. And yeah, so I think actually maybe I kind of fooled you into thinking that it's more complex than it is. But most of the time, actually, it's quite simple to predict the overall instance. Yep.
I'm waiting for the mic.
Ah, okay, great.
Sorry. Sorry.
So this is a very old example. If I post, for instance, when Elon Musk says, quote, Nazis rock, unquote, then he is aligning with the Nazis. Is that hate speech?
I'm not qualified to answer that. I don't know, it's quite a
Well,
tricky question.
let's assume that that Nazis rock is hate speech. Would my tweet be hate speech? And what I'm saying is I'm a little concerned with the loss of context in breaking things up into atoms.
Yeah, it's a great, great point. That is a challenge when you break things into atoms, that you lose this kind of context. And especially because, like I said, I insist on you must make predictions only for one atom without seeing the rest of the atoms, right? And there's plenty of cases where, well, to understand the meaning of that, you have a quote, the meaning of that you have to consider the wider context. And in my opinion, that's all about the right choice of atoms, right? So in this case, we shouldn't break this down any further, right? Because like it just doesn't make sense to consider that quote without the wider context around it. I think a good future direction, to be honest, would be to dynamically choose what these atoms are based on the example. So, like for example, I talked about generate spans, and maybe you maybe use nouns to break down the different input to spans. I think the model could learn itself how big the span could be, and that example the model could learn. But actually, no. I don't think we can just take this quote on its own. I think we have to consider the wider input. So I think this is a very tricky part. But I believe that, it's all about what's the right choice of atoms. And I think there's better ways of doing it that we haven't explored yet. Good follow-up? Oh, sorry. So you're not yet satisfied by that answer.
I want to know, would that be an automatic process of learning or an annotated one?
I'm not sure. I think that it automates in some way, but I don't yet have some ideas. But maybe if you ask me in a year's time, I might have a very kind of elegant, nice answer to that. So watch this space, I guess.
Yeah, so I was thinking if you are doing spans, it's a one connected interval, but the dependencies would be long term, like something from the beginning, there's something not related in the middle, and then both of those atoms come together and do.
Exactly. So I know I'm over time, so I'll just give a 20-second answer to that, and then I'll wrap up. I think it's exactly the same point, right? Like, how big should your atoms be? We solve this in our work with, we also consider consecutive atoms as a single atom as well to get around this problem. It wasn't a problem with the LLM generated facts, but I think this is still a challenge. How do you choose the right atoms? What we did works, but the work that we did, but I think there's definitely room for improvement, to be honest. So I really hope that other people will become encouraged to try and take this on further and come up with even better methods. Great, I think that's me for time.
Okay, thank you.
Thank you very much.